Ever try picturing, like, the temperature at every single point in your house?
Mm,
Not just by the thermostat, but, like, everywhere.
okay.
Or imagine mapping air quality across a whole city, block by block.
Yeah.
Talk about information overload. That's the wild world of spatial statistics. That's where today's deep dive takes us. We're wading into a paper called Bayesian Nonstationary Spatial Modeling for Very Large Data Sets.
Catchy.
Yeah, no need to memorize that. We'll call it the Flexible Maps paper for short.
And it's a paper addressing a real need because traditional stats, they get overwhelmed by this kind of data. They often assume things are stationary, basically behaving the same way everywhere.
Okay, so like, what does that even mean in practice, though?
Like saying soil in a rainforest is the same as in a desert. You wouldn't bet your garden on it, right?
Right, that's like using yesterday's weather to plan a year's worth of picnics.
Exactly.
So how do we make, like, better maps when things change so much from place to place? That's our so what here?
Yeah.
Not just the fancy stats, but, like, why should anyone care about getting this right?
Because bad maps lead to bad decisions.
Okay.
Imagine relying on a pollution map that doesn't account for how a factory impacts its surroundings differently.
Yeah.
You might end up with misguided cleanup efforts or worse, health risks in the wrong places.
The stakes are high.
Yeah.
We're talking about, like, understanding a process here,
Mm-hmm.
but not just like a to-do list.
Right.
What
Yeah.
exactly do we mean by a process in this context?
Picture it like this. A process describes how something changes over an area. Instead of just isolated measurements, we're trying to model the rules of how things vary.
Okay.
This could be rainfall across a county, the spread of a disease, even how much money people spend at different stores in a city.
Okay, so this non-stationarity thing, that's like saying those rules can change depending on where you are on the map.
Exactly. It's more the norm than the exception, really.
Huh.
Imagine soil types across a region.
Okay.
You could have clay-rich areas, perfect for certain crops, but right next door it's sandy, good for something completely different. A stationary model would average everything out, missing those crucial differences.
And suddenly farmers are planting the wrong things or using the wrong fertilizers based on this averaged out view.
Right.
That's a recipe for disaster,
Yeah,
both financially and environmentally.
precisely. And here's where it gets even more nuanced. It's not just about being right on average, it's also about knowing HOW, right or wrong.
Yeah.
We might be at any given spot on the map. That's where uncertainty quantification comes in.
Uncertainty, so it's like a confidence level attached to each prediction.
Yeah.
Not just what the model says, but
Yeah.
like how much we should trust it at that particular point.
You got it. If a model says there's a gold deposit under your house, but the uncertainty is huge, you probably wouldn't start digging just yet.
Probably not.
But if the uncertainty is low,
Okay.
you might be calling a mining company. That level of confidence, being able to quantify it, that is crucial for decision making.
So how does this flexible maps paper actually tackle these challenges? They throw around terms like covariance tapering and low-rank models.
Right.
Sounds a bit intimidating, to be honest.
It can seem that way, but the idea is actually quite elegant. Imagine trying to make a perfect replica of a giant, incredibly detailed sculpture.
Okay.
You could try to capture every single curve in detail,
Yeah,
but that would take forever and might not even be useful.
right.
Instead, you could focus on the overall shape and then, strategically add detail where it matters most.
Is it like simplifying without oversimplifying? You're not trying to recreate the entire thing, just capturing the essence.
Precisely. Covariance tapering and low-rank models are like techniques that help us achieve this simplification in the context of spatial data. Covariance tapering helps us focus on relationships between points that are close together, kind of like saying, let's not get bogged down with tiny details in areas that are miles apart.
Makes sense?
Yeah.
Why spend all your effort modeling the relationship between, like, my houseplant soil and the soil on the moon when they're clearly not affecting each other?
Exactly. And that's where low-rank models come in. They help us represent the most important information about these relationships in a very efficient way, which is crucial when you're dealing with massive data sets.
It's all about working smarter, not harder.
Right.
But there's one more piece of the puzzle, right?
Yeah.
They mentioned something called Gaussian processes.
Mm-hmm.
That sounds vaguely familiar, but I can't quite place it.
Think back to stats class.
Okay.
Remember the bell curve?
Yeah.
That's a Gaussian distribution. Now imagine stretching that bell curve out over our map. That's essentially what a Gaussian process does. It provides a flexible way to model how smoothly things change over space.
So instead of assuming everything changes at the same rate everywhere, the Gaussian process lets the data tell us where things are changing quickly and where they're more gradual.
Exactly. Now, the standard approach to using Gaussian processes for this kind of modeling is called the predictive process.
Okay.
And while it works well in some cases, it can struggle when we have those abrupt changes we talked about earlier, like our soil example.
Because it tries to smooth everything out, even when the reality is more like a patchwork quilt of different soil types.
A perfect analogy.
Yeah.
So this paper introduces a clever twist. They call it the tapered remainder component.
Tapered remainder. Okay, I'm intrigued. Break that down for me. What's so special about this component?
Imagine you've got that simplified sculpture we talked about.
Okay.
The overall shape is there, but it still needs some finer details. The tapered remainder component is like going back and adding those details, but only in the areas where they really matter.
So it's like we're zooming in on those areas where a simple, smooth curve just doesn't cut it.
Precisely. It's like having a regular map and then a magnifying glass to zoom in on the really important details. And this is what allows the model to capture both the large-scale patterns and those crucial local variations.
Okay, I'm liking this tapered remainder. It's like having your cake and eating it too.
Yeah.
Simplicity where you need it, detail where it counts. But this is where my brain starts to get a little fuzzy. The paper mentions using something called random knots. And honestly, it sounds a bit like something you'd find in a sailor's handbook, rather than a statistics paper.
It's a very evocative term for a powerful statistical tool. Think of these knots as anchor points for our model on that map we've been talking about.
Instead of just like randomly throwing darts at the map, these knots are strategically placed to give us the best possible picture of what's going on.
Precisely. And here's where the random part comes in. Instead of us, the researchers, deciding where to put those knots based on our assumptions, we let the data guide us. This helps avoid introducing our own biases.
So it's like letting the data speak for itself and tell us where it's most informative. I like it. But I have to ask, how do we know how many knots is enough?
Right.
Too many. And we're back to that overly complex model problem.
That's where the elegance of this approach really shines. Remember Occam's razor?
Yeah.
The idea that simpler explanations are usually better.
Right.
This model has that principle baked in. It naturally gravitates towards using the fewest knots possible while still capturing the complexity of the data.
So it's like finding the perfect balance, enough knots to be accurate but not so many, that the model becomes unwieldy.
Exactly.
It's like finding the sweet spot on a radio dial.
Yeah.
Clear signal, no static.
Exactly. And the best part is this paper doesn't just stop at the theoretical level. They actually put this method to the test using real-world data.
Oh, okay.
They used it to map soil variations in Australia.
Australian soil. That's a data set I can get behind. I mean, everyone's like dug a hole in the ground and seen how much it can change even within a few feet. But what makes the Australian soil so special?
Well, for one, it's huge. We're talking a massive data set with over 34,000 observations.
Wow.
Trying to analyze that with traditional methods would be a computational nightmare.
Yeah, I bet. And I'm guessing this non-stationary model with its clever knots and tapered remainders, it handled it like a champ.
Like a charm, indeed. But here's where it gets really interesting. The researchers weren't just mapping soil types. They were specifically looking at radioactivity levels as a way to figure out the clay content.
Hold on, radioactivity, that sounds a bit alarming. What does that have to do with clay?
It's not as scary as it sounds.
Okay, good.
It turns out certain radioactive elements tend to cling to clay particles in the soil. So by measuring radioactivity levels, the researchers could get a very precise picture of where the clay-rich soils were and how that varied across the Australian landscape.
Ah, so it's like X-ray vision for soil.
Yeah.
But why go through all that trouble? What's so important about knowing like where the clay is?
Clay content has a huge impact on agriculture. It affects things like drainage, nutrient retention, even what types of crops will grow well in a particular area.
Oh, wow.
Having a precise map of clay distribution is incredibly valuable for farmers.
Okay, that makes sense. Instead of relying on guesswork or doing endless soil tests, they can use this model to get a really detailed picture of their land. Talk about smart farming.
Precisely. And remember how we talked about uncertainty quantification?
Yeah.
This model doesn't just tell you where the clay-rich areas are. It also tells you how confident it is in its predictions for each location.
So a farmer can look at this map and see where the model is really certain about the clay content.
Right.
Those areas are probably good to go. But they can also see where there's more uncertainty. Those might be spots where they want to do some additional testing just to be sure.
Exactly. It's all about making informed decisions based on the best available data. And that's really the beauty of this whole approach. By embracing the complexity of real-world data, by acknowledging that things don't always change smoothly and predictably, we can build models that are both more accurate and more useful.
I love that. It's like we've graduated from those old school, like, one-size-fits-all maps to something much more nuanced and insightful. It's like having a GPS for understanding the world around us.
I couldn't have put it better myself.
So for anyone listening who's ever felt overwhelmed by the sheer volume of data in the world, remember this flexible maps paper. It's a great example of how the right statistical tools can help us cut through the noise and find the signal. By letting the data guide us, by embracing complexity, we can unlock a deeper understanding of the world around us. And that's it for today's deep dive. We'll see you next time.